Everyone, my name is Lydia, and this is what I wish they taught me about econometrics and introduction. We've seen that heteroskedasticity does not bias OLS coefficient, but it does affect something equally important, our inference, which means a coefficient can be perfectly unbiased and still completely misleading. And if we can't correctly measure, how uncertain we are about it. So what does inference rely on? When we run a regression, we rely on certain things. We rely on standard errors to measure precision. We rely on t-stats for hypothesis testing. We rely on confidence intervals to express uncertainty. And on p-values to make significance decisions. So all of these flow from one thing, the standard error. If the standard error is wrong, everything else in this list is also wrong. Now, where does the standard error formula come from? So the standard OLS standard error formula assumes, as we saw in the previous video once again, that the conditional variance of the error term on x is equal to sigma square. Okay, so this formula was derived under the assumption of constant variance, and it uses a single sigma square to summarize the spread of errors across all observations. Okay, this is also the formula you see in every regression output table, basically. And it is only valid when homoskedasticity holds. At the same time, from statistical property 2 of OLS, for instance, you had the exact formula for the variance of the beta 1 hat, which was sigma squared divided by the sum of xi minus x bar squared, where the sigma square, okay, was the variance of the error term, okay, the residual variance. So in that sense, for us to be able to make any claims about statistical property 2 at this point, if this sigma square is not constant across all of your x's, then which value should go into this? And this is the variance of the beta 1 hat, and we know that the standard error is just the square root of that variance. So as you can see, the problem starts from the variance in there, and then to standard error, and then cascades on t-stats, confidence intervals, and p-values, which use those same values to be constructed on, okay? And unfortunately, in real life situations, not all observations will be equal because some observations have low variability and they are very reliable, but other observations will have high variability, which means they are much noisier. And OLS is going to treat all of these observations equally in the same reliable way. So it's like averaging the opinions of experts and completely a random guesser and treating them both as equally informative. The results measure of uncertainty in this case will be miscalibrated. In terms of consequences of standard errors, so we know if the standard errors are too small, then it means we are overconfident. We think we know more than we do. And when they are too large, it means we are underconfident. Okay, so we think we know less than we actually do. And without correcting for heteroskedasticity, we don't know which direction the error goes. It depends on specific patterns of heteroskedasticity in the data. Okay. Although, as you will see when you work more and more exercises, the heteroskedasticity more often will produce standard errors that are too small, and in this case, leading to an over rejection of the null hypothesis. But again, keep in mind, this is not guaranteed. In terms of consequences for the other terms that we've seen here, the t-stat, the p-value, or the confidence interval, remember that t-statistics are constructed as your beta hat divided by the standard error of the beta hat. So obviously, if the standard error in here is questionable, the entire t-statistics will be questionable as well. P-values, they are constructed based on a t-value that you have. So if the t-value was questionable to begin with, your p-value will also be questionable. And for the confidence interval, because that is constructed using the standard error, again, we won't be able to rely on that expression of uncertainty that that confidence interval is giving us. So heteroskedasticity matters a lot in practice, okay? You might get an answer where the coefficient might be right, but if you're making, let's say, a business decision or a policy decision based on significance, because you're seeing whether the benefits way over the cost, then you could be acting on noise and taking the wrong decision in there, okay? Because once again, heteroskedasticity doesn't move the regression. It changes how confident you should be about where that line actually is. Heteroskedasticity makes standard errors incorrect. So it corrupts t-statistic p-values confidence intervals, even though the coefficients themselves are unbiased. In the next video, we'll learn how to detect heteroskedasticity in practice, and we'll use some formal tests to also do that. So stay tuned, and I'll see you in the next video.